Betelgeuse, the supernova, not the 1988 American fantasy horror / comedy film directed by Tim Burton, even though it's a good film, but it's not today's subject. Betelgeuse is a red supergiant of spectral type M1-2 and one of the largest stars visible to the naked eye. It is distinctly reddish, semi-regular variable star whose apparent magnitude, varying between positive 0.0 and positive 1.6, has the widest range display by any first magnitude star. At near-infrared wavelengths, Betelgeuse is the brightest star in the night sky. Its bare destination is Alpha Orionis. If it were at the center of our solar system, its surface would lie beyond the asteroid belt, and it would engulf the orbits of Mercury, Venus, Earth, and Mars. But nevertheless, there are several even larger stars in the Milky Way. The calculations of Betelgeuse's mass ranges from slightly under 10 to a little over 20 times that of the Sun. For various reasons, its distance has been really hard to measure. Currently, the best measures are on the order of 500 to 600 light years from the Sun, a wide uncertainty for a nearby star. Its absolute magnitude is about -6. Less than 10 million years old, Betelgeuse has evolved rapidly because of its large mass and is expected to end its evolution with a supernova explosion, most likely within the next 100,000 years. Having been ejected from its birthplace in the Orion OB1 association, which includes the stars in Orion's belt, this runaway star has been observed to be moving through the interstellar medium at a speed of 30 kilometers per second, creating a bow shock over 4 light years wide. In 1920, Betelgeuse became the first extrasolar star whose photosphere angular size was measured. Studies have reported an angular diameter ranging from 0.042 to 0.056 arc seconds. That range of determination is ascribed limb-darkening pulsations and varying appearances on different wavelengths. It is also surrounded by a complex asymmetric envelope, roughly 250 times the size of the star, caused by mass loss from the star itself. The Earth's observed angular diameter of Betelgeuse is exceeded only by those of R Doradus and the Sun. Starting in October 2019, Betelgeuse began to dim noticeably, and by mid-February 2020, its brightness had dropped by a factor of approximately 3, from magnitude 0.5 to 1.7. By February 22, 2020, Betelgeuse stopped dimming and started to brighten again, and as reported on February 25, 2022, has remained in a more normal brightness range. Infrared observations found no significant change in brightness over the last 50 years, suggesting that the dimming was due to a change in extinction, or large grain circumstellar dust, rather than an underlying change in the luminosity of the star. A 2022 study against the Hubble Space Telescope suggests that occulting dust was created by surface mass ejection. This surface mass ejection cast material millions of miles from the star that then cooled to form the dust that caused the star's dimming. In 2016, the International Astronomical Union organized a working group on star names, WGSN, to catalog and standardize proper names for stars. The WGSN's first bulletin of July 2016 included a table of first two batches of names approved by the WGSN, which included Betelgeuse for this star. So it is now entered in the IAU catalog of star names. Betelgeuse is a very large, luminous, but cool star, classified as an M1-2 red supergiant. The letter M in this designation means that it is a red star belonging to the M spectral class, and therefore has a relatively low photospheric temperature. The luminosity class indicates that it is an intermediate luminosity supergiant, with properties partway between a normal supergiant and a luminous supergiant. Since 1943, the spectrum of Betelgeuse has served as one of the stable anchor points by which other stars are classified. Uncertainty in the star's surface temperature, diameter, and distance make it difficult to achieve a precise measurement of Betelgeuse's luminosity. But research from 2012 quotes a luminosity of around 126,000. Studies since 2001 report effective temperatures ranging from 3,250 to 3,690 degrees. Values outside this range have previously been reported, and much of the variations is believed to be real due to pulsations in the atmosphere. The star is also a slow rotator, and the most recent velocity recorded was 5.45 kilometers per second, much slower than Antares, which has a rotational velocity of 20 kilometers per second. The rotation period depends on Betelgeuse's size and orientation to Earth, but it has been calculated to take 36 years to turn on its axis, inclined at an angle of around 60 degrees to the Earth. In 2004, astronomers using computer simulations speculated that even if Betelgeuse is not rotating, it might exhibit large-scale magnetic activity in its extended atmosphere, a factor where even a moderately strong fields could have a meaningful influence over the star's dust, wind, and mass loss properties. A series of spectropolarimetric observations obtained in 2010 with the Barnard telescope at Pic du Midi Observatory revealed the presence of a weak magnetic field at the surface of Betelgeuse, suggesting that the giant convective motions of supergiant stars are able to trigger the onset of a small-scale dynamo theory. Betelgeuse has no known orbital companions, so its mass cannot be calculated by that direct method. Modern mass estimates from theoretical modeling have produced values of 9.5 to 21 solar mass, with values of 5 to 30 solar mass from older studies. It has been calculated that Betelgeuse began its life as a star of 15 to 20 solar mass, based on a solar luminosity of 90,000 to 150,000. A novel method of determining the supergiant's mass was proposed in 2011, arguing for a current stellar mass of 11.6, with an upper limit of 16.6 and a lower of 7.7 solar mass. Model fitting to evolutionary tracks give a current mass of 19.4 to 19.7 solar mass from an initial mass of 20. The kinematics of Betelgeuse are complex. The age of Class M supergiants with an initial mass of 20 is roughly 10 million years. Starting from its present position and motion a projection back in time would place Betelgeuse around 290 parsecs further from the galactic plane, an implausible location, as there is no star formation region there. However, Betelgeuse's projected pathway does not appear to intersect with a 25 Aura subassociation, or the far younger ONC, particularly since very long baseline array astrometry yields a distance from Betelgeuse to the ONC of between 389 and 414 parsecs. Consequently, it is likely that Betelgeuse has not always had its current motion through space, but has changed course at one time or another. Possibly the result of a nearby stellar explosion, an observation by the Herschel Space Observatory in January 2013 revealed that the star's winds are crashing against the surrounding interstellar medium. The most likely star formation scenario for Betelgeuse is that it is a runaway star from the Orion OB1 association, originally a member of a high-mass multiple system with Ori OB1A. Betelgeuse was probably formed about 10 to 12 million years ago, but has evolved rapidly due to its high mass. In 2015, H. Boya and J. Owes suggested that Betelgeuse may instead be a member of the newly discovered Taurian OB association. In the late phase of stellar evolution, massive stars like Betelgeuse exhibit high rates of mass loss, possibly as much as one solar mass every 10,000 years, resulting in a complex circumstellar environment that is constantly in flux. In a 2009 paper, stellar mass loss was cited as the key to understanding the evolution of the universe, from the earliest cosmological times to the current epoch, and of planet formation and the formation of life itself. However, the physical mechanism is not well understood. When Martin Schwarzschild first proposed his theory of huge convection cells, he argued it was the likely cause of mass loss in evolved supergiants like Betelgeuse. Recent work has corroborated these hypotheses, yet there are still uncertainties about the structure of their convections, the mechanism of their mass loss, the way dust forms in their extended atmosphere, and the conditions which precipitate their dramatic finale as a Type II supernova. In 2001, Graham Harper estimated a stellar wind at 0.03 solar mass every 10,000 years. But research since 2009 has provided evidence of episodic mass loss, making any total figure for Betelgeuse uncertain. Current observations suggest that a star like Betelgeuse may spend a portion of its lifetime as a red supergiant, but then cross back across the H-R diagram, pass once again through a brief yellow supergiant phase, and then explode as a blue supergiant. Astronomers may be close to solving this mystery. They noticed a large plume of gas extending at least 6 times its stellar radius, indicating that Betelgeuse is not shedding matter evenly in all directions. The plume's presence implies that the spherical symmetry of the star's photosphere, often observed in the infrared, is not preserved in its close environment. Asymmetry of a stellar disk has been reported at different wavelengths. However, due to the refined capabilities of the telescope's adaptive optics, these asymmetries have came into focus. The two mechanisms that could cause such asymmetrical mass loss were large-scale convection cells or polar mass loss, possibly due to rotation. Probing deeper with ESO's amber gas as the supergiant's extended atmosphere has been observed vigorously moving up and down, creating bubbles as large as the supergiant itself, leading his team to conclude that such stellar upheaval is behind the massive plume ejection observed by Caravella. In addition to the photosphere, 6 other components of Betelgeuse's atmosphere has now been identified. They are an environment otherwise known as the MOL sphere, a gaseous envelope, a chromosphere, a dust environment, and 2 outer shells, S1 and S2, composed of carbon monoxide. Some of these elements are known to be asymmetric while others overlap. The first claim of dust shells surrounding Betelgeuse was put forth in 1977, when it was noted that the dust shells around mature stars often emit large amounts of radiation in excess of the photospheric contribution. Using interferometry, it was concluded that the red supergiant emits most of its excess radiation from positions beyond 12 stellar radii, or roughly the distance of the Kuiper belt at 50 to 60 AU, which depends on the assumed stellar radius. Since then, there have been studies done of this dust envelope at varying wavelengths and getting different results. Studies from the 1900s have estimated the inner radius of the dust shell anywhere from 0.5 to 1.0 arc seconds, or 100 to 200 astronomical units. These studies point out that the dust environment surrounding Betelgeuse is not static. In 1994, it was reported that Betelgeuse undergoes periodic decades-long dust production, followed by inactivity. In 1997, significant changes in the dust shell's morphology in 1 year were noted, suggesting that the shell is asymmetrically eliminated by a stellar radiation field strongly affected by the existence of photospheric hotspots. The 1984 report of a giant asymmetric dust shell, which is 206,265 astronomical units, has not been corroborated by recent studies, although another published the same year said that 3 dust shells were found extending 4 light years from one side of the decaying star, suggesting that Betelgeuse sheds its outer layers as it moves. Although the exact size of the 2 outer carbon monoxide shells remains exclusive, preliminary estimates suggest that one shell extends from about 1.5 to 4.0 arc seconds, and the other expands as far as 7.0 arc seconds. Betelgeuse is traveling supersonically through the interstellar medium at a speed of 30 kilometers per second, creating a bow shock. The shock is not created by the star, but by its powerful stellar wind, as it ejects vast amounts of gas into the interstellar medium at a speed of 17 kilometers per second, heating the material surrounding the star, thereby making it visible in infrared light. Because Betelgeuse is so bright, it was only in 1997 that the bow shock was first imaged. The cometary structure is estimated to be at least 1 parsec wide, assuming a distance of 643 light years. Hydrodynamic simulations of the bow shock made in 2012 indicate that it is very young, less than 30,000 years old, suggesting two possibilities. One, that Betelgeuse moved into a region of the interstellar medium with different properties only recently. Or two, that Betelgeuse has undergone a significant transformation, producing a changed stellar wind. A 2012 paper proposed that this phenomenon was caused by Betelgeuse transitioning from a blue supergiant to a red supergiant. There is evidence that in the late evolutionary stage of a star like Betelgeuse, such stars may undergo rapid transitions from red to blue and vice versa on the Hertzsprung-Russell diagram, with accompanying rapid changes to their stellar winds and bow shocks. However, if future research bears out this hypothesis, Betelgeuse may prove to have traveled across 200,000 astronomical units as a red supergiant, scattering as much as 3 solar mass along its trajectory. And ladies and gentlemen, that is all I have on Betelgeuse today. Thank y'all for taking your time to watch this video, and please don't forget to like and subscribe, and y'all have a wonderful day.
All of this is research found on the internet.